In this video we're going to take a look at fixed and floating point binary numbers. So the whole point of fixed and floating point is to represent decimal numbers in binary. So fixed point is where we've got a predetermined position where our decimal point is, which means we can't change that at all. There's only going to be a set amount of numbers we can have and a set amount of accuracy. So here we've got all these numbers on the screen and we've got past the decimal point, you just divide by 2. So 1 divided by 2 is 0.5, 0.5 divided by 2 is 0.25, and so on. So we've got a half and a quarter there. So we are limited in how many numbers we can use, especially if that 32 is going to be the sign bit, then we can only represent 31.75. So we can't really make a very big number, which is where the pitfalls, the downfall of a fixed point number system is. You can't change how accurate, you can't change how big. So we've got a small number here, so we can't really make anything big at all, but we've got a little bit more accuracy. So we're still sacrificing sort of size of the number and accuracy. So if every single number was in the same format, you're really limited. Whereas floating point, each individual number can be represented with a bigger decimal amount or a bigger positive amount, which is great. Okay, so floating point allows us to create either really big numbers that aren't very accurate or really accurate numbers that aren't very big. So we've got that flexibility. So we split it into a thing called the mantissa, which is the number to the left. Well, I'm saying on to the left. The mantissa is the actual whole number, but usually in the exam they represent it on the left and the right, not usually as one big number. There's normally a space. So the mantissa is the number itself, and the exponent is how much do we move the decimal point by. So if you've got a really big exponent, you've got a really small number, but it's really accurate. If you've got a really big mantissa, it's not very accurate, but it's really big. So it's really flexible and adaptable. So we've got an example here where we've got our sign bit, our mantissa, and our exponent. Now the decimal point always starts to the right of the sign bit, or the first bit on the left. Okay, then you calculate the exponent. So in this case it's 3, which means this moves 1, 2, 3 places. Okay, that means that the number is 1 plus 4, which is 5, plus the 0.5 and the 1.25. Sorry, the 0.125, which gives us 5.625. Because that's what the actual number looks like there. It looks like this one. So that's what the real number is. However, if we wanted a more accurate number, the exponent just needs to change, which is where it becomes really, really useful. So, an example here, we've got 0.110110. So you've got a space, and then we've got that. This is how the exam will represent the answer. So they'll have the mantissa and the exponent separately, and they'll tell you that the mantissa is however many bits, in this case it's 8, and the exponent is 4. That's the most common, but it can change. I've seen 7 and 3s and all sorts. Okay, so you write down the mantissa. You can then calculate the exponent, which in this case is 4. That means we know that this number can go 1, 2, 3, 4 places. So it's going to be 1101.100, and we can then calculate the answer. So if you've got a negative number though, you'll notice that the sign bit will be a 1, just like looking at sign and magnitude. Okay, so we've got a negative mantissa and a positive exponent. So what we need to do is find the 2's complement of the mantissa, translate the exponent, move the decimal point, and then calculate the answer. So hopefully you did that. So the mantissa was 0.110, which is 2 plus 4, which is 6, and then we've got 0.5 and 0.25, so it's 6.75, but obviously we have to choose complement, which means it's minus 6.75. So let's get another one here. So we've got 0.101.011, 0.101. So you need to find the 2's complement. We need to translate the exponent, move the binary 0.5 places, and you should have got minus 21.25. Now if you've got a negative exponent, this is where it can get a bit confusing. You'll know that because it begins with a 1 again. Okay, so you just convert it as normal. You don't have to change the mantissa or anything. The number stays the same. but you convert the exponent. Once you've done that, you can then move the decimal point as normal, but because you've 2's complemented it, the decimal point will move to the left instead of the right. Okay. So if we think about this number here, if we 2's complement it, it's going to be 1 is actually an exponent of -1. Okay, so it means instead of moving that way, you're going to move 1 space to the left. So it says if the exponent is negative, the binary point must be moved left instead of right. So we've got a -1 there. So what we need to do is move. It looks like we've got a really big one there, but we convert it again. So we've got that's 2, so it's -2. So we'd actually move the decimal place 2 places to the left, which makes it 0.0011000. So we've got a really accurate number there, but we've only represented it in so many bits, which is really useful. So now we're going to take a look at how we do some of these floating point numbers in an exam situation. So we've got the mantissa, which is the main number, and the exponent is how much the decimal point moves. So first things first, what we do is we write out the mantissa. So we've got 0, 1, 0, 0, 1, 1. Now that number itself is irrelevant. We don't know what it is. Now the decimal point always starts here. Okay? So what we do now is work out this exponent. So that's the mantissa. The exponent, by looks of things, is 4. Okay? So what this means is that this decimal point is going to move 4 places to the right because it's a positive number. So 1, 2, 3, 4. Okay? So what the number actually means is 0, 1, 0, 0, 1.01. We can then calculate the answer. So this is the ones column, 2, 4, 8, 16. And this is 0.5 and 0.25. So decimal point wise, this way you times by 2. That way you're dividing by 2. Okay, so this number is 8 plus 1, so we've got 9.25. And that is your answer, and that's how we get a decimal number in binary.